Here we're determining which of the following statements are true, and you're given the statement that this electron configuration is supposed to be the excited state electron configuration for titanium. So taking a look at the periodic table, we can locate where titanium is, which is here where my mouse is hovering. And you can see that it has all filled orbitals until 4s1. So 4s starts over here. So, and 3d2, 4s2 and 3d2 will take you to a neutral species for titanium. And it's saying that the excited state electron configuration is 4s1 and 3d2. So one thing to note is that there's a difference between excited state and an ionized titanium. So if titanium is ionized, it would lose one of the electrons here. So yes, this configuration would make sense for Ti+. But for excited state, your electron is still in the element or in the atom, so it doesn't go anywhere, so you should still see it present. So the statement is false. So moving on, looking at this, it says the ground state electron configuration for the undiscovered element 115 is this. And if we take a look at where that is on the periodic table, 115 is located here. It's moscovium, which I think has been discovered now. So if you take a look and try to figure out what the electron configuration is, if you go out one period, go all the way to the right, you have your noble state shorthand, noble gas shorthand to be Rn, radon. And if you start counting electrons from left to right, yes, you do indeed get 7s2. And if you go over to the f orbitals, this starts at 4, this is 5, you have 14 electrons because the f orbitals have 7 different orbitals and 2 electrons can go in each, so 7 times 2 is 14. And for your d electrons, you start counting 3, 4, 5, 6. So for this row, you get 6 d electrons, 10 electrons. And finally, we're at the p block, and in order to get to 115, you count 1, 2, 3. So you get 7p3. So yes, this is true. This is the electron configuration. Moving on, if an element abbreviated X has a ground state electron configuration of neon 3s2, 3p4, then the formula of the compound that X forms of sodium is sodium X. So let's take a look at the periodic table to determine which element this electron configuration refers to for the ground state. So looking here, it says it's neon, so we locate neon, and it's 3s2. And then we move over, we have 3p4, so count 1, 2, 3, 4, so s. So we know because s is in this group, it is usually found to have a 2- charge. Whereas if you are, this is a molecule where sodium and X is in the 1-to-1 ratio, sodium usually takes on a +1 charge, so this would not be balanced. So the statement is false. So next we have the element with the ground state electron configuration of this is an alkaline earth metal. So let's take a look at where the periodic table, let's take a look at the periodic table and locate where the alkaline earth metals are. And they are here, group 2. So anything with electron configuration that ends here is an alkaline earth metal. So let's take a look. So you have 1s1, 2s2, and then 2p6, and then 3s2. So you end at magnesium. So yes, because it is in this group, it is an alkaline earth metal. So the statement is true. Next, we have the ground state electron configuration for copper is argon 4s1 3d10. So remember, argon for copper, it has one of those weirder configurations where it is one of the exceptions to the electron configuration rules. So taking a look at the periodic table, we're here. We go at 1. Yes, argon is our noble gas shorthand. We have 4s2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons in order to get to copper. Because of our exception, our s orbital is only half filled because it likes to be half filled and completely filled if possible. And we move 1 electron into the copper because your d orbitals are in a slightly lower energy than your s orbitals. So it's better to have less electrons in the higher energy state because it's better for the entire atom to be lower energy overall. So the statement is true. Next, we have the element with a ground state electron configuration of krypton 5s2, 4d10, 5p5 has 10 valence electrons. So valence electrons are all the electrons that come after this noble gas shorthand here. So if we count here, we have 2, 10, and 5. So we actually have 17 valence electrons. So this question, or this statement, is actually false.